Hello?
Perfect. Yeah, we can see your slides.
Sound check.
We can hear you. You can go ahead.
Can you see me?
Yeah.
Good afternoon over there. My name is Konstantinos Servicinos-Bam. I am a CSIRO data scientist working at POSI Supercomputing Center, and I'm going to claim that we can sometimes use machine learning to replace space missions. So here's what we have done in our case. We have, I'll take you on a small journey. We've done crater counting. Why we do crater counting? Well, we can estimate the age of planetary surfaces using the intuition that the more craters, the older the surface. Of course, that's not just an intuition. It's been shown. Secondary crater mapping is key to identifying injection site of a Martian meteorites. In this particular case, a large enough event that can cause material to be ejected with enough velocity to escape Mars would also cause a ray pattern of secondaries. So when we examine those, we can find out exactly possibly where we have an ejection site was. For other cases, we can learn more about Mercury and Ceres, where we have applied this algorithm. In this particular case, we've identified some ejection sites for potential sample that for a potential meteorite that we have found here on Earth. This has been possible by using exactly this mapping of meteorites. This is an ordinary map of Mars. This is a map that we have produced by looking at exactly the same locations, and you can see ray patterns. But by examining these ray patterns, we can find very violent candidate sites for ejections of meteorites. The evaluation challenges for when we use machine learning to map craters are similar to when we use experts and volunteer identifications, and experts between them, they don't seem to necessarily agree very well and they have up to 20% difference even between experts. These results indicate that the validation and training can be challenging, but an ML-based approach can be useful, but we need to keep in mind, as I say here, that the traditional measure of precision and recall will be low, and the final result will need to be validated independently using independently labeled dataset. The challenges for our crater detection algorithm is, first of all, we need fast labeling. Experts would already take a few seconds to mark a crater, but that would not make it possible for us to have the databases that we require. Yeah, the speed difference is our primary concern. We have previous versions that we've of our crater detection algorithm. We have a monolithic container that we have applied on Themis data. We have a shell script that we applied on Jezero crater, and in this case, we've used Nextflow. Nextflow is a system we borrowed from bioinformatics and provides modularity, reusability, configuration, injection, and many other advantages. Now, in CDA, we have 4 main tasks. We have georeferencing. We take a raw image from an orbiter and we produce a georeferenced tile. We use it to train our algorithm, and we use it for inference in order to produce a CSV, which contains the craters, and we use it for annotation, as you can see on this image. Main characteristics of the architecture of the main machine learning workhorse is we have a convolutional neural network. We got this ready. It's called YOLO. It's an object detection algorithm that we have trained and adjusted to our purposes. It's a very interesting case of object detection, and it was the first that it will perform the labeling at once in a very fast way. Its intention was to be used in self-driving cars, so in real-time applications. So in our case, we have millions of images as we need to be evaluated. So that made sense as a choice. It has also very good performance. So training. For our training, we use the high resolution imaging science experiment. We have which is on board the Mars Reconnaissance Orbiter. It was important to retrain because we want to get down to very short, very small scales. And eventually, when you get to very small scales, you have other non-circular features. The user operator was also interesting for a recent Mars mission that was launched by NASA. Evaluating the final result was by labeling the intended target data set from a context camera, also from the Mars Reconnaissance Orbiter. We also manually mapped another 2,000 craters, and we found out that an overall F1 score of 0.75 for evaluating using CTX. Bear in mind that we set the intersection over union for considering some crater as the same to 0.3 for this ratio. The inference was challenging. We have a very big computer, but still it took a little bit of time. We have 15,000 original images. We need to downsample each image to 40 meters per pixel and 160 meters per pixel. So we end up with a total of 45,000 images. For each image, we break it down into tiles. Depending on the size, this can be up to 2,000 tiles. We need to mark each tile producing 0 to 100 detections on each. So, and later we untile the result. So we bring this back to the original frame. We use a non-max suppression algorithm on the groups of 9 adjacent tiles to make sure that we don't have any duplicates. This is an overview of what happens in our workflow. We have a high resolution GeoTIFF that comes in, that represents the entire scene, and we have many of those scenes. We downsample it. And the reason we do need to downsample it is because obviously some craters are larger than would fit in a scene, so we need to catch those as well and include them in our database. Later, we will tile the image into what is the input for our YOLO algorithm. Then we do our object detection, and then we perform finally the non-max suppression. This is an execution graph that comes out of Nextflow. This is very interesting piece of framework that we can use from bioinformatics. We used the now retired Magnus computer. It's a computer that has worked really well for large-scale CPU workloads. Just to make it short, here's where we believe this. We have good reasons to believe that this a rock that we found from Mars, or many rocks that we found from Mars, came from. And as I said in the opening, this kind of replaces at least one mission, as we don't currently have a sample return mission, and we know where this sample came from. So we can the significance. There's some significance about the evolution of Mars. There was a major thermal anomaly that's been active in the Tharsis region throughout the history of Mars. There are some other very interesting conclusions can be drawn out of this. I think I've gone over time. There is another. Sorry. There is another rock that we have found from another crater, and in this case, the Karatha crater. And finally, we are going ahead and looking at the moon, and we're multiple bodies together to find out if there are differences in the meteoritic flux in between them, and there are some other that are pending publication. Thank you very much.
Thank you, Konstantinos. We have time for a few questions. Do we have people in the room with questions? Okay, we have one question here. Oh. Okay, yeah.
Hello, Elena Dominguez from Fesca speaking. It wasn't clear to me what was the input to your neural network, like single images for each crater or a full tile with different craters?
Oh, okay. We have a tile that would look like this. That is what is coming into the YOLO neural network, and YOLO will mark for each one of those tiles all the craters or the circular features that that can be found that are craters. This in this case is a 960 by 960 pixel tile, and I don't know if I can point with my mouse. I hope you can see what I'm pointing at. Here,
are you sharing your screen? Sorry.
sorry. I do apologize. I've been answering without sharing screen. Maybe now you can see a little bit better.
Yeah, now we can see it.
All right. This is the tile I'm referring to. This is a 960 by 960 pixel tile. And the algorithm in this case will mark all the craters. This fits exactly in one, two, three, third step, as you can see in this workflow. And each image needs to be cut down into these tiles, and then we have some work to do to bring back the pixel coordinates to the scene coordinates and to geographical coordinates. So the input is the 960 by 960 tiles.
Great, thank you. Do we have questions in New York?
Hi, thanks so much for the talk. Just really on this slide as well, I was interested in how much kind of technical work went into the engineering of the pipeline here, like the ability to process this many images, for example. Could you talk a little like sociologically how you arrange for the, did you recruit any software engineers? How did you arrange for that kind of time? Like what was the kind of process to do that engineering work?
Okay, well, in this case, I have rewritten this two latest version of this myself. Have retrained. This is a multidisciplinary team. So that was my part, the actual analysis of cosmic ray exposures, other elements of that lead us to constrain actually the ejection site. Were not done by me, but this particular one, that's me.
Well done. Thank you.
Thank you.
I think we can thank again Konstantinos.